Efficient transportation is becoming a necessity as population growth increases. Poor infrastructure can affect the quality of life and economic productivity in urban environments. Our project aims at creating a virtual system that can increase the efficiency of traffic flow in a given intersection. It involves designing and assembling a VI that could be used in intersections where traffic changes drastically around the clock. Our system would simply count the number of vehicles entering an intersection, detect and prioritize oncoming emergency vehicles, and instruct the traffic lights to change accordingly. This will be achieved with the aid of two devices. We will use cameras to identify and count incoming vehicles and unidirectional microphones to detect the sound on the emergency vehicles. LabVIEW will be a central part of this project as it will host the image and sound processing units that will analyze images from the camera and filter the sound from the microphones.
In our smart detection system, the two key sensors we are using are webcams and unidirectional microphones to capture the quantity of vehicles in their respective lanes and to determine the type of vehicle, whether it be emergency or casual. The main sensor to acquire the number of cars is the webcam. The webcam is a device that uses an image sensor chip to capture moving images and convert them into digital signals that can be processed in our program. In order to gather quality images, an array of lenses is built around the sensor to focus the parallel light into it. Typically, webcams will use complementary metal oxide semiconductors, which convert the charge from the photosensitive pixel on the sensor into a voltage which allows us to manipulate in LabVIEW. The second sensor we will be using will be a microphone to determine the type of vehicle. The specific microphone we are using is a unidirectional type to mitigate the surrounding noise from the environment and isolate as much as possible the noise coming from each side of the road. In our analog electric microphone, the main sensing build is the diaphragm, which is composed of electret. Electret is a ferroelectric material that is permanently polarized. The diaphragm has the freedom to move at the center and responds to the pressure created by sound. Behind the diaphragm will be a stationary metal plate to create a capacitor that is used to measure the distance between the two materials. The change in distance will cause a change in voltage, which is equivalent to the pressure of the sound wave. The microphone can sense this because the electric has a fixed charge, and any change will denote a sound wave. The output voltage from the microphone is small, so an amplification device will be required. So to simplify our system, it will be broken up into 4 different stages or blocks. The first stage will be the sensor stage, then comes the signal conditioning stage, the reading and recording stage, and lastly the outputs. So the first stage will be the sensing stage, where the webcam and the microphone will be used to gather quantifiable data that we can manipulate in our LabVIEW program. Before we gather feasible data though, the sensors must go through a signal conditioning stage. For webcams, image processing must be used to isolate each car in each side of the road. Using LabVIEW, we are able to detect bright objects, which will represent a vehicle. For the microphone, a bandpass filter will be used to isolate a certain frequency level that represents the loud siren of an ambulance, for example. Since the output voltages will be small, an amplifier will be used. In the third stage, the main logic and manipulation of the data gathered is performed. The information from the webcam and the microphone will be sent into the NI-DAC and measure the voltage and sent into our LabVIEW program. The LabVIEW program will process the data sent into it and finally change the traffic lights to enable higher traffic efficiency based on the logic of our program.
Hey guys, this is Kagan. So this is the virtual representation of our program. This is the front panel where it can be monitored and controlled using the different panels. This is the virtual representation of the intersection. This is the live camera feed coming from the camera. This is the sound processing algorithms that we are using to detect emergency vehicles. For testing and demonstration purposes, we are using still images to test our VI and demonstrate the logic. In this first simulated case, we are demonstrating regular traffic on a main 4-lane road and a single vehicle entering from a side road. VI allows a single car to pass by turning the main light red and the side light green that can be demonstrated over here. In this scenario, we are demonstrating heavy traffic flow through the intersection. More than two vehicles are entering from side road, as well as there are more than three vehicles on a main road. In this scenario, a traffic signal cycles through the green, yellow, red light for each direction and does not rely on number of vehicles. Now I'm going to demonstrate the emergency vehicle coming through the intersection using the 4 kilohertz sound frequency. So now you can see when the emergency sound is detected, the emergency indicator turns red, as well as the traffic signal blinks red light, so that all vehicle can be stopped and emergency vehicle can pass through intersection easily and efficiently. This is our system block diagram where our logic actually works. The first loop you can see right over here is a while loop, and that controls the traffic signal. It has multiple cases that works according to the signal received from sound processing and image processing loops down below. So the second loop you can see here is a sound processing loop that acquires the sound signal and then process it, and then using the filter we filter out all the frequencies but the 4 kilohertz frequency, so that whenever the threshold is reached, it triggers the emergency alarm and sends the signal to our traffic control system. The third loop you can see here is the image processing loop, and it acquires the image. Right now we are using the still image, but the live camera feed can be fed to the same loop from here. And once the live camera feed or the still image are detected, this process is the object detection machine learning technology of LabVIEW and detects the number of vehicles on the road and send the signal to the traffic management loop for the further analysis. Now that we have understand how our measurement system works, let's go through some of the limitations and error it might experience during the operation. So first, let's discuss about the limitations of camera. The placement of the camera can be challenging, and it might determine how far a system can look for the vehicles. The second limitations of using cameras are weather. Since the vision is dependent on rainfall, snow, and fog, it can significantly affect the performance of the measurement system and its accuracy. The other limitation we have is for this project, we are assuming that cars are bright objects and can be easily seen using the camera. But in real life scenario, the cars can be any color including black. That might be tough to determine using the cameras. Now, let's talk about some of the error it might present. When any debris that is bright in color fly close to the camera, specifically snow, it might trigger the false positive and increase the number of cars in some specific direction when there are no cars. Now let's go through the limitations of using microphone. Since microphone, since we are using microphone to detect the emergency vehicle, anyone can play a specific soundtrack of emergency vehicle and trick the signal into experiencing emergency and blinking and causing a public nuisance. The other problem it might have is excessive wind can temporarily render microphones ineffective due to generating a lot of noise and preventing microphones from detecting the true emergency vehicle noise.
Potential applications. So one of our potential applications is to detect the sound of a doorbell. If you are someone who is constantly wearing a noise-canceling headset or a gaming headset, you sometimes might not hear the doorbell. So with our VI, we will detect the sound of the doorbell and notify a smartphone that is connected to it or another device that's just always near you. Another potential application we have is in parking lots. Driving around a parking lot just to see that there are no spaces is the worst thing about parking. So, with our VI, we will use the car counter to track the cars coming in and leaving the parking lot. And with this information, we will show the number of cars in the parking lot in the color red to indicate the lot is full, and in green if there's still empty spaces to park in. This will save people time from driving around only to realize that the lot is full. Our last potential application is for the in-home fire alarms system. If a person is deaf, they cannot hear the alarm going off, so with our VI, we will track the high-pitched noise, and when detected by the system, it will notify a connected smartphone or another electronic device that could be visually seen.